Okay, so we've now finished talking about amplitude modulation. In lecture 7 and 8, we'll be talking about angle modulation. Although angle modulation starts with the letter A, we're not talking about AM anymore. We're talking now about FM. So whenever we say FM, for short, what we mean is FM and PM. So phase modulation and frequency modulation. And as we're about to see, frequency and phase are closely related. So this is the first of 2 lectures about angle modulation. Last week, we finished off talking about DSB, and we spoke about the demodulation of DSB. We introduced something called a coherent demodulator, or a coherent detector. So the block diagram on the left, that's a DSB modulator. The diagram on the right is the coherent demodulator, or coherent detector. So this signal here travels across the channel and is received here. And this is the demodulator. And this message here, we hope, is closely related to this message here. It will never be exactly the same because it will have suffered noise, attenuation, distortion, interference, other effects. And one of those other effects is the effect of the demodulator itself. We spoke last week about the possibility of an error, frequency and phase errors at the receiver. So we said the local oscillator in the receiver could have a phase error, delta phi, or a frequency error, delta f or delta omega. We spoke about how this would affect our recovered message. We said a phase error would result in an attenuation or a scaling down of our message. And a frequency error would result in a beating effect. So it's as if it's modulated by a very low frequency audio wave. Now today we're going to be talking about frequency modulation. So instead of having the amplitude of the carrier to change, we want the actual frequency of the carrier to change. And that's a harder concept to imagine. It's harder to visualize. How will the frequency actually change with time? How is the instantaneous frequency going to change? So on Monday, we will carry on talking about frequency modulation, but we'll talk about demodulation. We'll also talk about bandwidth effects, but we'll talk about demodulation. On Tuesday, that's your class test. Okay, 1 o'clock on Tuesday is your class test. So we're going to meet twice next week. There won't be a class on Thursday. Okay, so we're going to meet on Monday for the demodulation, class test on Tuesday, nothing on Thursday. The class test includes everything we've covered up to and including DSB. So it doesn't include lectures 7 onwards. It's lectures 1, 2, 3, 4, 5, 6, and all the problem classes. Okay? That's what's covered in the class test. So this is where we are now. Next week we'll do demodulation, and then the last 4 lectures of the module we'll be talking about digital communication. So we'll talk about the bridge, digitization, familiar lecture to you, and then we'll talk about digital modulation. Our class test is on Tuesday. Okay, sorry to keep reminding you about this, but it's important you all know that the class test isn't happening during our normal timetabled session. It's happening on Tuesday. It should be in your timetable. Okay? If it isn't in your timetable, get in touch. Okay, practice mini test is already online. Okay, I've put up 10 questions online. The actual test is 15 questions, and you have 1 hour to complete them. Okay? If you spend half of that 1 hour flicking through your lecture notes and opening Kahoots and trying to watch YouTube videos, you're not going to have enough time. Okay? So 15 questions in 1 hour, that's not a lot of time. Okay? So I don't need you to tell me that there wasn't enough time, because I'm telling you, there isn't enough time. There's only enough time if you're prepared. Some questions are so easy you can answer in 5 seconds. Multiple choice, click, 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 click. It's easier than the Kahoots. But some questions, you need to do some calculations. So some questions you can do in 10 seconds, some might take 5 minutes. But you have enough time, okay? Last year, the average time was 49 minutes, okay? That's how long it took students last year to do the 15 questions, 49 minutes. What does that tell you? It tells you that some people didn't have enough time to finish, okay? But it also says that many people finished before 49 minutes, okay? So just be prepared. I've given you everything you need to be prepared. You have the problem sheets, you have the Kahoot, you have a few YouTubes, you have a practice test, okay? The average mark last year, the average mark was 12 out of 15, okay? That was the average mark last year, okay? The questions are the same. Okay, so the only thing that's changed is you. So I've given you every opportunity to do really well at this test. I want you all to do really well at this test. Okay, I want you to go into the exam with enough coursework to be confident and not anxious when you sit that exam. Okay, so there's 2 tests worth 15% each. So potentially you have 30% going into the exam. I've set up a separate discussion board on Vital for any questions about the class test, before the class test or after the class test. Okay, so if after the class test you're not happy about something, you have a question about something, you want clarification about something, put it on that separate discussion board, just so that we don't get the 2 boards confused. Okay, so angle modulation, we've spoken about all this, we know how that works, but how does frequency modulation work? How are we going to change the frequency in real time? How is the frequency going to track the amplitude? So amplitude tracking amplitude makes sense visually, mathematically. Frequency tracking amplitude isn't as intuitive. It's not as easy. And when we talk about phase modulation, that's even less clear. So look at the FM signal, look at the PM signal. They're almost exactly the same, aren't they? So here, when the amplitude of the original message, or the envelope here, is maximum at the top, the frequency looks like it's a minimum. So the frequency and phase, appear to be out of phase. So what's changing in the frequency is the instantaneous frequency is changing. What's happening in the phase is the instantaneous phase is changing. We'll talk about the relationship between phase and frequency in a minute. So FM radios, they're all around you. Okay, so FM radio could be a cheap portable radio, it could be a radio in a car, it could be a fixed radio, part of a stereo. Whether you use a radio or not, radios are all around you. And FM is usually what people listen to music on. Okay, so if someone's listening to music and it's not streamed over the internet, it's probably FM rather than AM. Why do you think that is? Well, perhaps this question will help you think about that. AM and FM, they're both analog signals, so they're susceptible to noise. But one is more susceptible than the other. One is more vulnerable to noise than the other. One suffers the effects of noise more than the other. Which one is it? Which is more susceptible to noise, FM or AM? So which will exhibit degradation or a reduction in quality due to noise more than the other. Now, if you think about it, AM, the information is encoded within the amplitude, whereas in FM, the information is encoded in the frequency. So the amplitude is constant. So in an FM signal, it's the instantaneous frequency that contains the information. So if noise adds itself to the signal, if it adds itself here, if it changes the amplitude, that'll have a greater effect on AM. Because AM, we are relying either on tracing this envelope or on recovering that message through a coherent detector. So the amplitude is everything for AM. In FM, the amplitude doesn't matter. The amplitude is constant. So in FM, adding noise will affect the amplitude, but it won't affect the quality of the signal. So FM does suffer from noise, but not as much as AM. So if you listen to music on an FM radio station, the quality is better for two reasons. What are those two reasons? Reason number one, I just said, because it's less susceptible to noise. Reason number two, because, anyone? Why does music sound better on FM? Because there are better radio stations. No, just kidding. Because it's a wider bandwidth. FM uses a wider message bandwidth than AM. AM will have a narrower bandwidth. So you're only listening to, potentially, lower frequencies. So the whole range of frequencies you'll get in FM. Plus FM, most radio stations, most music radio stations on FM are in stereo. So you get a left channel and a right channel. That also adds to the quality. So these are all reasons why music sounds better on FM. I'm not happy with the 43% who still say FM is more susceptible to noise. So which one is, when I say susceptible, I mean more vulnerable. It's more affected, less protected. So which is more susceptible? AM is more susceptible. FM can resist noise because the amplitude is constant. Or a better way of saying that is because we're not interested in the amplitude. Okay, so I guess 57% of you don't believe me. So angle modulation, that's what we mean when we say FM. It's a form of angle modulation. So these are some of the advantages and some of the disadvantages. We say it's a more effective use of power. You can see why, because there's no wastage of power. There's no carrier. In FM, all of the signal is the message. Whereas in AM, you can have two sidebands and you can have a carrier. Better signal quality, we've given a couple of reasons why that is, but the most important reason for the quality is because it's less susceptible to noise. Disadvantage is we usually have a greater bandwidth, and there are two reasons for that. We'll speak about that next week. And there's a smaller range, and the range is related to the higher frequencies we use, not the modulation format, okay? So the smaller range is because FM operates at higher frequencies in the megahertz. So it's 88 to 108 megahertz. So look at S of t. The amplitude is constant. Look what's happening to the frequency. Fi, that's the instantaneous frequency. That's the frequency at any instant in time. Now for AM, the instantaneous frequency is always Fc. But here, the instantaneous frequency is FC plus something else. And that something else is related to the message. Okay? So if MFT is big at that instant in time, the instantaneous frequency will be much bigger than FC. If the message is 0 at a particular instant in time, the instantaneous frequency will be exactly equal to the carrier frequency, if that's 0. And here we have this sensitivity, which says how much we're going to vary the frequency. Is it very sensitive? Will it change a lot? Or change a little? Now we're going to introduce KF, but we're never going to use it. We're going to use something else called the modulation index, and we'll talk about that in a minute. Quick question for you. We said FM radio is all around you. Is there an FM radio in your mobile phone? There's supposed to be a graphic. I don't know why it's not showing up. But is there an FM radio in your mobile phone? Some mobile phones have FM radios, some don't. Does your phone have an FM radio? If you don't know, find out. Something about 5743. So if you have an iPhone and it's older than the iPhone 7, then it does include an FM radio. So you have an FM demodulator and you just have to plug in the headphones and you can listen to free FM. iPhone 7s onwards don't have that. Okay? All other phones, you need to check. Do you have an FM receiver? Usually, you have a native app that comes built in on your phone, and if you run it, it asks you to plug in the headphones. So, most of you here do have an FM radio, okay? Quick question. If you don't have an FM radio, why do you think that's the case? Why would a phone 20 years old have a radio? Don't know what happened to that video. That was just a demonstration of an ancient phone changing radio station on the phone. So phones have had radios for years. Why have they stopped including radios in mobiles today? Well, they haven't, but Apple has, and some other manufacturers have. Why do you think that's the case? I thought iTunes didn't exist either. Okay, so can someone say something positive about FM radio? Someone stick up for FM. There must be at least one redeeming factor. Is there anything good at all about FM? Anyone? Can anyone say something good about FM? Okay, two good reasons why there is pressure on the manufacturers to enable the FM chip. One is that FM is always available, even if your network isn't available. So right now you're probably connected to the nearest cellular tower on campus or close to campus. But if there's any problem and that tower goes out of operation, or there's too much congestion, or there's some problem with your network anywhere in the network causing you to lose signal, and if it's an emergency situation, if there's an earthquake, a volcano, a pandemic, an explosion, if there's some kind of natural disaster, and you need access to emergency information, the only place to get that is the radio. And we each carry a high-tech communication device around us in our pockets, so potentially we have life-saving information through the radio. Another reason is it's free. You don't have to pay subscription. You don't need a data connection. It's not eating into your data allowance. You have free music, okay? Free news, free emergency information, potentially free traffic information. So I do a lot of driving. I drive to work. Motorway driving. I'm always listening to the radio. And it's free. And it doesn't matter if there's network coverage in the mountains or on the motorway, wherever I go, there's almost always radio coverage. Okay? But you've all been quite, well, most of you have been quite generous in your reasons. None of you has been cynical and said that the phone manufacturers benefit from you using data to stream your media. Okay, so you said stream instead, but actually, if you think about it, there is a commercial incentive for companies like Apple to disable the chip. So the chip has always been available in iPhones, but they've disabled it to force you to use media. Just like companies like Motorola back in the early 2000s, they disabled Bluetooth on their phones. Bluetooth worked, but you couldn't use Bluetooth to send media. If you wanted to send a picture to a friend, you'd have to use data because Bluetooth was free. Okay, so sometimes there's very cynical commercial reasons why these things are the way they are. Okay, back to our lecture. There's only two things I want to tell you today, and that's one of them. Okay? So in every lecture, I have 2 or 3 important points, and I try to tell you when they come up. This is the important point for today. Frequency and phase. One is the derivative of the other. So one is the derivative of the other is the integral of the first. Which way round is it? Is frequency the derivative of the phase, or is phase the derivative of the frequency? Have a think about that. If you get this question right, that's 50% of today's lecture. Okay? It happens to be true, and we'll look at why in a second. So, let's look at FM. If you think of the phase, phi of t, as being a function of the message signal m of t, so directly proportional, so phi of t is just some factor multiplied by m of t, that's what we call phase modulation. But if the phase is the integral of the message, we call that frequency modulation. And you can go backwards and say if the instantaneous frequency, or the instantaneous frequency is the derivative of the phase. The 2 pi is just to get this in hertz rather than in radians per second. So now we've introduced 2 things, something called the instantaneous frequency, something called the instantaneous phase. So if you have a carrier frequency and you have an instantaneous frequency, and they're not the same, the instantaneous frequency is always deviating. It's always oscillating from the carrier frequency. So you have a carrier frequency of, say, 100 megahertz, then you have an instantaneous frequency. It's 101, well, 100 point something, or 99 point something. So it's deviating on either side of the carrier frequency. So carrier frequency, and then instantaneous frequency. The instantaneous frequency can be higher, can be lower. And if you take the maximum deviation, the maximum difference between the instantaneous frequency and the carrier frequency, we call that the frequency deviation. So the frequency deviation is the difference, or the highest difference, the maximum difference between the instantaneous frequency and the carrier frequency. Not the difference between the highest and the lowest. That, twice delta F, we call that the frequency swing. So the frequency swing is the highest frequency minus the lowest frequency. But the maximum deviation from the carrier frequency is called delta F, the frequency deviation. And if you divide that frequency deviation by your original bandwidth, the message bandwidth, that ratio is called the modulation index, beta, a unitless quantity that indicates the depth of modulation. So in amplitude modulation, we would compare amplitudes. Remember we said A max minus A min divided by A max plus A min. So we're comparing amplitudes. In frequency modulation, we're dividing frequencies. So we divide the depth of modulation. Sorry, we divide the frequency deviation. That's the instantaneous frequency minus the carrier frequency. We divide that by the message bandwidth. We end up with something called beta, modulation index. Now, the modulation index for FM can be and often is greater than 1, but it also can be less than 1. Okay, so we have this ratio of delta F. We don't have to say max. We can just call it delta F. So delta F divided by baseband bandwidth. That's the second thing we wanted to cover today. Okay? So the two things we wanted to speak about today is the frequency being the derivative of the phase, and the modulation index being the ratio between the instantaneous frequency minus the carrier frequency, that's delta F, to the baseband bandwidth, W. Now, that was FM. Now let's look at PM. PM slightly easier in the sense that your phase here is being added to what we would normally consider the carrier component. So instead of having delta F or delta omega, now we're talking about delta phi. And delta phi is the maximum value of the difference between the original phase and the phase with this added phi of t. So the modulation index for PM is just delta phi. We don't need to divide it by anything. So compare that with FM, where it's delta F over the baseband bandwidth, W. Here it's just delta phi. So remember, when we spoke about AM, we spoke about modulation, demodulation, bandwidth, and power. Same for FM. I'm going to talk about modulation today, demodulation next week, bandwidth next week, and power today. Okay? Power in FM is so easy, we can summarize it in one sentence. The power doesn't change. Okay? Because we have a constant amplitude, only a changing frequency, power doesn't change. So power for a sine wave is proportional to the amplitude, not the frequency. Okay? So the frequency doesn't affect the power of a sine wave. Don't confuse that with an electromagnetic wave where the energy is proportional to the frequency. So the power of a sine wave depends only on the amplitude, so it's proportional to the amplitude squared. Because we don't have an envelope, the power doesn't change. Quick question. Consider this here. We have a cosine, omega ct, that's my carrier. Sine 1000, that's my message, or some function of my message, depending on whether we're looking at FM or PM. So for FM, the message is part of the argument for the sine or the cosine. It's part of that phase. My question is, what's the power? Should I be looking at the 6? Should I be looking at the 2? Should I be looking at omega c or at 1000 pi? We should be looking only at the 6. So the power is proportional to that 6 squared. So it's 6 squared divided by 2. Well done. Okay, less obvious now. Look at this signal. Where's the message? It's not clear where the message is, but it's somewhere here. Okay, for now, let's just say the message is something to do with these two. The question is, what's the maximum phase deviation? So how far will the phase deviate So if both of these signs happen to be 0 at t equals 0, then you'll have 6 cosine omega ct. Let's consider that to be your 0 phase. So any deviation from that is what we're looking for. So what's the biggest deviation? It can deviate by up to 2 plus 10 equals 12 radians. That's the maximum deviation from omega ct. Okay, let's go through this in a bit more detail. So this is the first example, 100% if you got that right. This is the second. So we're looking at the maximum phase deviation, delta phi, or delta phi max. So we're taking the difference between the instantaneous phase and the carrier phase. And it's when these two happen to coincide and have their peaks, so 10 plus 2, 12 radians. Next example. This time we're looking at frequency deviation. Okay? Find the maximum frequency deviation of the same signal. Now remember, instantaneous frequency is the derivative of the instantaneous phase. So Fi is simply the derivative of the phase. The phase is the bit between the brackets. All of that, all that angle, that's the phase. The only reason we divide it by 2 pi is to get it in hertz rather than radians per second. So you take the angle between brackets, take the derivative, divide by 2 pi, that's your instantaneous frequency. You need to subtract the carrier frequency, Fc, or omega c divided by 2 pi. Why do I subtract that? Because I'm trying to find the frequency deviation. Remember we said it's how far it deviates from the carrier frequency. So you subtract the carrier frequency. That's how you find the deviation. So if you subtract this Fc term, you end up with 2,000 over 2 pi plus 20,000 over 2 pi. In this case, it's 3.5 kilohertz. Do I have enough information to find the modulation index? Remember, modulation index beta is simply delta F, which we just found, divided by the message bandwidth. Do we know the message bandwidth? Well, it's going to be related to one of these two numbers. The lower or the higher? Well, clearly the higher of the two. So it's related to the 2000, so it'll be 2000 over 2 pi. That's your message bandwidth. So we can find beta, but we're not going to do that right now. That's a summary of what we've covered today. Phase is the integral of frequency, or frequency is the derivative of the phase. And what I haven't included on this summary is the modulation index beta. Beta is delta F divided by W. Okay, so a few new concepts we covered today. We'll look at it in more detail. We'll look at the spectral considerations, something called Carlson's rule, and we'll look at demodulation of FM next week. Good luck for the class test on Tuesday. Prepare for that. We're not having a problem class before that, but there are plenty of practice questions online. Make use of that. Any questions, use the discussion board, and I'll see you all on Monday. Take a second, please, to leave some feedback. Sorry, I missed a couple of questions. Somebody asked, what is PM? PM is phase modulation. So PM is phase modulation, where the phase, or the angle of the sine wave, changes in proportion with the message, not the frequency. Are both phase modulation and frequency modulation angle modulation? Yes. When we say angle modulation, we're talking about both PM and FM.